Hello, my name is Joel Esposito. I'm a professor at the United States Naval Academy, and one of the things I do there is I mentor about 20 undergraduate researchers a year as they prepare to work with other advisors and they're trying to construct their first research proposal. And every year we see some really excellent presentations, but there's always some things we can all do better. So today I'm going to talk a little bit about how you can deliver a nice research proposal presentation, especially in engineering, although I think some of the advice is applicable to other kinds of technical talks too. So I think the best way to teach this is by example. So I'm going to give an example of a really bad talk, and you are going to feel free to roast me in the chat, drop some comments, make some remarks, tell me what I can do better, tell me what I did awful. And then we'll kind of break down what went wrong, and then we'll come back around and we'll try to do it all over again, only much, much better. And we'll see some really good practices and some tips. So I hope in doing so, I don't put you through the 4 stages of PowerPoint briefs, but let's get started with the bad one. So I'd like to welcome my audience. My name's Joel Esposito, and this is my research proposal, control of a USV. An outline of my talk. First, I will give some motivation for the talk. Then I will do the literature review. Then I will discuss my problem statement. I'll show you some of my demonstration, which includes my plan for my activities of next year, as well as a Gantt chart and a budget. And then I'll take questions. Motivation. So the reason why I want to study this topic is because USVs are becoming really important in the Navy. And it's important that we learn to control them, but it's hard. There's a lot of challenges there that have been identified. So it would be really good if we had a better way to control the velocity of these vehicles. I was required to do a literature review for this project, and I read 7 papers, and these are the details if you'd like to look any of them up. And my problem statement is going to be specifically that the goal of this project is to design a controller for small unmanned surface ships operating in a riverine environment subject to current, waves, and other realistic conditions. A major, though not insurmountable challenge comes about in not having precise values of the drag coefficients, often referred to as Cx, Cy, and Cz. We believe this control law that we're proposing can stabilize the vehicle in spite of parameter uncertainties and disturbances. So one of the things we'll have to do is some drag testing, and we're going to do that, collect some data in a facility that we have here at the Naval Academy. And then my plan for next year is a 3-part plan. I'm going to prove that my control law works. Then I'm going to make a simulation to test that out. And that simulation is going to be based on Newton's law. And then I'm going to build an actual unmanned surface vessel, and I'm going to test it out in a creek nearby our campus. This is a copy of a Gantt chart for my project. It's a schedule or a timeline. You can see I have all the activities listed here and mapped out on the calendar. Here's my budget. The total budget for this project is about $29,000. I'll end now, and I'll take some questions from the audience. I'm sure you have a lot. Well, what do you think about that? Do you think I did a good job? Do you think that was an effective presentation? I put a lot of work into it. That summarized about 4 months worth of work preparing for my proposal. Or do you think there's things I could do better? I think there's probably a lot of things we can do better, don't you? So let's give it another try. Or perhaps first we should look back and analyze what we did wrong. So the first thing here is the title slide. This title slide is liable to be up for quite some time. Title slides are often just sit up there while you're introduced to the audience. Will you find your bearings? Will you make some adjustments to your configuration around you? So the question is Is this how you want to give a first impression to the audience? Or said another way, how does this title slide help you? What do I see here? I see an acronym. It's not defined, so right away, people might not know what I'm talking about. The title, which just says control, is not very specific. It doesn't say I want to control the velocity or the heading or anything like that. There's no graphics on here that help my audience orient themselves to what it is I'm about to talk about. I have my name up here, but there's no contact information if somebody wants to follow up with me later. So overall, this title slide, remember now, I only have 10 slides in this slide deck. So this is about a 10th or 10% of my presentation, and I'm getting very little informational content here. Again, I have an outline slide. I submit that if your talk is anything less than a half hour, there's no need for you to have an outline slide. By having carefully crafted headings and a logical flow, your audience will be able to pick up on where they are in the talk. Certainly, for a 5 or 10 minute talk with only 10 slides, I wouldn't dedicate 10% of my presentation time to this slide. There's very little information here. If you have to do an outline, you might consider making a graphical map and repeating that throughout the transitions in the presentation to help the audience orient themselves to where they are. I had a motivation slide here, and there was a few things going on. The first was this rather distracting animation came in. It really doesn't add a lot of value, and it's a bit gimmicky. But the other item is that there's no non-obvious information here. If you know anything about unmanned vehicles, robotics, or control systems, you probably know that there's a trend towards automating vehicles and they need control systems, and it can be difficult. I didn't tell the audience anything that I learned in my reading. I didn't give them any specific facts, scenarios, challenges. My graphic is small, and it's not directly related to what I want to do. Sure, it's a ship, but it's not an unmanned ship, and it's not illustrating any of these challenges. Oh, and by the way, I used the wrong version of the verb it's. Literature review. So the first thing you need to know is when you give an academic talk, there's no greater sin than omitting a literature review slide. So you must have one, not just because your professor said so, but because that's what research is. It shows how you're building on the state of the art. Also, as a courtesy to the people who came before you, it's important to acknowledge their contributions. As you move along in your career, often those people will be audience members. So it's important to acknowledge them. However, this is a terrible example of a literature review slide. I can guarantee you that no one in the audience wants to actually read all these details. No one will write down a page number or a publisher or anything like that. Instead, what you should be telling them is, how do these works inform your own? What are the pros and cons or the strengths and weaknesses of the different works and how they fit together, preferably in a format that's easy to digest in 30 seconds to 1 minute. The problem statement. This is actually a pretty good problem statement, and it's entirely appropriate for a written document, but it's not for a presentation. It's a lot to digest in a minute for the audience. There's just too many full sentences here, punctuation. There's even kind of very, very pretentious subordinate clauses. A major, though not insurmountable challenge. Come on. On top of that, this gimmick of, because it's a maritime application of kind of using this ocean scene as the background, but with this poor choice of blue and white font, makes it really difficult for the audience to see. There's no graphic here to help. Overall, I think this is a terrible problem statement slide. Here, I want to talk a little bit about how drag testing works, but I don't know what this is a picture of. If you've never been in a tow tank, it's unlikely you even know what's going on here. There's a plot to the right, but the axes aren't labeled, and I don't have any substantive discussion of it. Here's my demonstration plan. Remember, the demonstration plan is the plan of all the activities you plan to engage in next year. For that reason, it should definitely take up more than a single slide in your slide deck. In fact, the majority of the slides should be related to the demonstration plan. There's completely insufficient detail. I don't give the audience any sense of how I plan to prove my control law works. I don't have to have all the answers here, but I should show I've thought out a plan. Likewise, in terms of building my boat, I don't give a parts list. I don't explain how the pieces will fit together. I don't explain any of the technical considerations or the building blocks of my simulation. I have an equation here, but I don't really explain the terms. I just assume the audience is familiar with Newton's law. And here's a picture of a boat, but it's certainly not the one that I'm going to build. That looks like a stock photo of a guy fishing. Once again, not a good use of my slides. Here's my schedule. It can be really challenging to present schedules. Again, what's appropriate for a written document may be entirely inappropriate for a visual presentation that the audience has to digest in real time. Things like an exact start and finish date, an exact duration, these kind of details in the font that they're displayed in are unlikely to be absorbed by your audience. On top of that, you want to think about each slide as occupying valuable real estate in your presentation. So the question is, why is all this white space here? Don't you think we could make this graphic significantly larger at the least and help people see what's going on? Likewise, on the title, ask yourself, why are you including a title? Is it just because the PowerPoint template made you? Was your audience just automatically know that this was a schedule of activities, presuming it was larger? If you didn't have that heading there, think about those issues. Think about how to use all the space on your slide. Same thing with the budget. It's very small. The quality is low because it was screenshotted, apparently. There's all this white space that's not used for anything. I don't really discuss anything interesting about the budget, and I give the total cost number of $29,000, which is often driven by labor and overhead, which are outside of my control. I spend no time talking about my parts list or the design decisions I've made. If you have to distribute something like this, certainly make it larger, consider highlighting the important parts, and perhaps make a handout for your audience. Finally, I think the worst slide of all is the question slide. Remember, the Q&A session, you hope, should be long and lively. It may go on for 5 minutes or more. Do you want to leave that slide up there for your audience to remember you by? I don't think so. Is there anything on here that's going to help me as a visual aid in answering questions of the audience or perhaps anticipating some? No. Is there any contact information on here in case someone is perhaps too shy or doesn't have time to answer a question and wants to follow up? Again, there's not. So I think we can do this a lot better for all those reasons and more. So what follows is going to be the same presentation, meaning the same project, but we're going to see a different set of slides and a different explanation. Let's give it a try. I hope you think I do better. Good morning. My name is Joel Esposito. I'm at the United States Naval Academy. And today I'm going to talk about a velocity control of an unmanned surface vessel, which we're going to abbreviate as a USV with uncertain drag coefficients. So just to give you a sense of the kind of problem I'm interested in, the Navy is increasingly using unmanned surface ships. And many of the mission sets require controlling the velocity of them in a very tight range. But doing so requires a good model of the drag force that the water exerts against the ship. And those can be notoriously hard to calculate in a precise fashion. So what I want to do is I want to design a control law formula that's going to help me set the rudder and the thrust so that, for example, if I'm in this creek and I want to navigate directly upstream, I can just kind of put those things in and the controller will maintain the desired velocity to within some very tight bounds, even though I don't have an exact model of the drag of the boat. So for my motivation, I spent some time reading this 75-page document that the Navy publishes once every 10 years, which outlines their strategic vision for how unmanned systems are going to be used. And you might not know this, but the Navy plans to add over 1,200 USVs over the next decade between now and 2030. So they're going to become a huge component of the future fighting force. And in that document, they identified 3 important challenges. And those challenges all require good velocity control. So on the left here, you see an example of what they call formation control. This would be a series of, say, patrol boats or protective craft maintaining a desired spacing. And in order to do that, of course, they have to have matching velocities. Otherwise, they won't be able to maintain the formation. Another major challenge they identified is recovery, which means recovering a small unmanned vessel from the back of a larger Navy ship, in this case, the littoral combat ship. And you can imagine if that docking is going to happen while both ships are in motion, it's very important they have matching speeds. If the USV is moving too quick, it could rear end the vessel. If it's going too slow, it won't be able to be recovered. And the final application they identify that requires good velocity control is mapping of the ocean floor. Here, a vehicle would move along at a very slow and steady speed, taking side scan sonar images of the bottom, and all those images have to be stitched together in a large panorama, and that becomes difficult to do if the speed's varying wildly. So for all these reasons and more, we've decided this is a really important problem for the Navy. I'm going to talk a little bit now about drag models for boats and why they can be difficult to measure. So this equation that you see on the top, this is the most common drag model in literature. And let me walk you through some of the terms. So there's a term called C1 and C2, and these are unknown. These are the things that I have to either measure or estimate, or maybe my control law is going to adapt to. But these are unknown parameters, but they reflect things like is the bottom of the boat smooth, or is the cross-sectional area large, or is the hull very sleek? Does it cut through the water easily? And these terms are the coefficients of the boat's forward velocity. So it's the linear velocity as well as the velocity squared. And those are variables that can be measured. There's usually a sensor on the boat that can measure your velocity. So then the challenge would be if you can estimate these drag coefficients and you can measure your velocity, then you can use this formula to predict the drag force, set your thrust to overcome it, and maintain a steady velocity. The way people typically measure these drag coefficients is they would take a scale model of their craft, and they would use a facility called a tow tank. And in that tank, what happens is there's a motorized gantry, kind of a rack above the tank, right? And it tows or literally pulls along the model at a constant known velocity. And in the connection between the gantry and the scale model, there are some force sensors there, and they're constantly capturing data about the drag force. So in this case, we'll have now measured or controlled the green variable, which is the velocity, because we know how fast this is moving forward. And we will have measured the force, which is F drag on the left side, the equation. And then we can try to solve for or fit data to get those coefficients. And we might get a plot like this where we're plotting our forward velocity, and then the drag force is measured, and there's some noisy data there, but we fit a model to it. The reason why that's not totally sufficient for field scenarios is that might give us a ballpark, but that ballpark can deviate quite a bit in practice for two reasons. One is that the cross-sectional area of the boat that's below the waterline can vary from laboratory conditions. So you can imagine as fuel is expended, as crew gets on and off the boat, or the mission payload changes, the weight changes, and that changes the displacement. Another issue is biofouling of the bottom. So barnacles and algae can build up there and kind of detract from how sleek the coating is and increase the drag. So this technique above gives us a baseline measurement, but we know that we could be off by, say plus or minus 10% because of these issues on the bottom. So my literature review, I read about 8 papers, and in doing so, I kind of partitioned them into a few categories. So on the left, these are 3 really good approaches to velocity control of surface ships. And those papers, they're all assume, though, that the drag coefficients are known. So they're really good control laws. I would like to make a control law like that has that type of performance, but they assume the drag coefficient's known, and I don't know my drag coefficients. Now, on the right side of this literature review, you can see some works where they designed an algorithm to estimate the drag coefficients online, meaning as the vehicle was moving in the water. But that's not used for control. That's just parameter identification. So my work is going to kind of unify these two fields or sit at the overlap of them. It's in the middle, it's shown that we want to do velocity control with unknown drag coefficients. So we want to control the velocity while adapting to or learning what the drag coefficients may be. The closest related work to mine is a work by my advisor, Professor Bishop, who used a learning control law to accomplish this task. And it's really good, and we're going to build on that. But one shortcoming of that work is they weren't able to show the range of drag coefficients, like how uncertain can you be, plus or minus 10%, plus or minus 20%, before the control law breaks or stops working. So we're going to build upon that by designing something that works in a pretty specific range, and we're going to demonstrate that in a few ways. So that led me to my problem statement. Every research problem involves studying some property of a particular process. So in my case, the process I'm going to look at is a novel adaptive velocity controller for USVs. Anytime I have a control law or an algorithm, I could think about what are the inputs, what are the known information, what's the outputs. So in terms of inputs, I'm going to have sensor information with my latitude, my longitude, my heading. I'm going to assume I know the mass and moment of inertia of the boat, but I'm going to estimate online this drag coefficient. So I have an initial ballpark estimate for it, but it's going to be adapted as the boat drives. In terms of outputs, my control law is going to produce a command to the propeller, the thrust setting, and the rudder setting that's going to help with my steering. So an example of kind of what that might look like is in this control systems diagram here, where we can see that there's a gain that's constantly adapting. Some of the parameters like the mass are known, and perhaps we have some external disturbances coming into play there too. The property that I'm going to show in my demonstration is that that control law has a zero steady state velocity error, even when there's 10% uncertainty in the drag coefficients. And even if there's mild disturbances like a 5-knot wind. So the way you would show that property is ultimately we want to make a plot that shows as time goes on that the velocity converges on the desired velocity. There might be some oscillation, there might be some overshoot as we kind of learn what the drag coefficients are and we adapt to them, but ultimately this gets to and stays on the desired velocity. So moving to the demonstration, that's going to be the bulk of my activities next year is going to be to demonstrate this. One of the first things I'm going to try to do is prove that the control law is stable. And the way I'm going to do that is I'm going to use something called Lyapunov's method. This is a common technique that I came across in the related work. And while I haven't worked out all the details, I'm going to show you an outline of what the proof might look like. So the first step is to formulate something that's like a kinetic energy function, except instead of having the velocity squared, it's the velocity error squared. And you can imagine if I plotted this function, it would be bowl-shaped like this. And down here at the very bottom is when the errors are 0. Everywhere else, the error is higher. My next step would be to take the time derivative of that function. I know the velocities change with time, so I can do that. I can take the time derivative. And then I'm going to substitute my control law in there for the forces on the boat. And based on that, I'm going to have more specific expressions governing how the error changes and how that Lyapunov function, this kinetic energy-like function, changes. And then finally, the goal is to show that the derivative of the error is always negative, which means that the error is constantly decreasing. And if that happens, then you can prove that eventually it will get to 0. So hopefully what happens is something like this. I start out, my velocity error is pretty high. And then as you can see, as time goes on, it's constantly, even though it may be oscillating, it's decreasing, it's getting lower. And finally, it achieves a stable minimum at 0. Oops, I don't know how that got in there. So next, my simulations. I'm going to simulate this controller before I go out and test it in the water. And this control systems diagram shows how the pieces of my system fit together. So here's my controller. And again, it's to be derived, to be determined. I don't have an equation for it yet, but that's the bulk of my work, is to do that. But the diagram shows what the inputs and outputs are. So if you think of this as a function, a bit of code that I have to write, the inputs to the control law will be my speed error and my heading error. And the outputs of the control law will be my propeller speed and the rudder or the motor angle if it's an outboard engine. However, I can't simulate the controller in isolation. I need some other components to work with here. I need a dynamic model of the boat itself. And for that, I'm going to use the one given in Fosun's seminal 2005 book. I also need a trajectory generator, something to give the desired velocities to keep me going along a path. So I'm going to use the one in Latome's book, published in 1999. On the bottom here, I show you my plan for the simulations I want to do. I'm going to simulate the controller's behavior with uncertainty in the drag coefficients between negative 10% and positive 10% uncertainty. So 5 different levels for the drag coefficients. I'm going to use 2 different types of trajectories, one constant velocity where the boat moves in a straight line, and the other where the boat's moving in an arc, a time-varying velocity that requires different accelerations. For each combination of trajectory and drag coefficient, I'm going to do 3 simulations with random initial conditions. So I want to make sure that for different headings or different starting velocities that this works. So in all, if you add that up, if you do the math, that's 30 simulations that I plan to report on. The experimental platform, the final piece of my demonstration is going to be to construct a small unmanned surface ship and then actually take it out in the creek and do some testing with it. So I've already identified a parts list, and around the perimeter here, you see some of the parts that I've identified. And in the center, you see what we call a functional block diagram that shows the pieces or the components I'm going to use, but also how they're interconnected and what information gets shared between them. So for example, I have my 2 12-volt marine batteries, and they'll be electrically connected to my amplifier. The amplifier requires 24 volts, so that's why I have 2 batteries. But then it shifts that to be between negative 12 and positive 12 volts and supplies that to the motor, which is going to produce thrust on this 12-foot aluminum John boat. There's more details in my written presentation, in my written proposal, but this gives you a sense of the parts that I'm using. For any experiment, if we're trying to show that a property like velocity control it holds, if we're trying to show that that's stable, we need a way to measure velocity that's at least as accurate as we expect our controller to be. So for that, we're going to use a piece of equipment called a real-time kinematic GPS. So this is a GPS system that has a local base station that provides a correction to the satellite errors over a small area. It's often used in agricultural applications, but it's also great for what we want to do because we're in a creek. We can set this up on the shoreline and use it to provide position estimates and velocity estimates in a small area. And you can get 5-centimeter position accuracy, a 20 hertz update rate, so 20 times a second, and velocity estimates to within 1/10 of a meter per second, which we think is more than sufficient for our application. For my experiments, they'll be conducted on College Creek. You see on the map here where I plan to set up the GPS base stations. I'm going to have a couple scenarios, one in which I move parallel to the current, the other in which I move perpendicular to the current, just to kind of, illustrate that the control system is capable of adapting to those scenarios. So just to recap my demonstration plan, there's 3 pieces of it. They each provide some strengths and weaknesses. So I have a proof. One of the nice things about the proof is that I can really show that it's stable for any drag coefficient or initial condition. I can leave that as a variable. Also, it's safe. There's no risk of equipment loss. If I find an error in my control law, I can diagnose it then. Some of the drawbacks of the proof are that it may not be easy to conduct the proof with that full nonlinear drag model, and it certainly ignores a lot of the real-world implementation issues. To get over some of those, I'm going to do a simulation also. And the benefit of the simulation is I can study that nonlinear drag model, and I can look at many scenarios in a short amount of time. And again, I don't have to worry about risking the equipment by taking it out in the field just yet. Some of the drawbacks of it is, again, it's not as realistic as a true experiment. And there's only a finite number of simulations I could do. Even though I'm going to do 30, I can't actually test it for every possible initial condition in the way I could in the proof. And then finally, I talked about the proof of concept experiment. We're going to construct the USV, and the real benefit of that is it's the most realistic scenario. There's realistic drag forces, there's wind, there's current. So it's very realistic. The drawbacks of that are there's certain things I can't control. I can't actually control what the current is on a given day or what the wind is on a given day. So there's some risk and there's some both in terms of time, but also in terms of anytime you take electronics out into the maritime environment, there's risks there. So those three pieces fit together and they complement each other in some nice ways. In terms of risks, every project has risks, especially in terms of time. So one of the things that I did is I selected this GPS system in this boat to be items that the department already owns. So I won't have to worry about supply chain issues or waiting for those things to arrive. And another risk mitigation strategy I did was I'm moving up the timeline for construction so that I can perhaps get out on the water and do some testing in late October before the creek freezes up. In terms of guarding against equipment loss, which is always a concern with autonomous vehicles, the simulation will let me build some confidence in my controller before I go outside. And I'll always have a person on board. It'll never be fully autonomous. There'll be someone there ready to take over if a collision looks imminent or if the control system goes unstable. And finally, safety. I need to consider the safety of both personal property and people. So that person on the boat will always have a personal flotation device. There'll be a buddy system where there's someone on the shore operating the GPS repeater, and I'll make sure to inform the harbor master and the crew team. And with these strategies, I believe I moved most of my risks to the green zone, which is low probability of occurrence or low impact. Here's a copy of my budget. Most of the budget is dominated by labor and overhead, but the materials item category is interesting. So let's take a look at that. The materials add up to about $23,000, but $22,700 of that is items that are already in stock. That is the John boat and the GPS system. But we will purchase a couple additional items. There's a small GPS to be mounted on the boat, as well as a commercial autopilot that total about $300. And I have details for why those parts were selected in my written proposal. Here's my timeline. So you can kind of see just at the 20,000 foot view level what my months are going to be spent doing. A couple interesting things to point out here. The construction of the experimental platform is going to start early to exploit the fact that the machine shop tends to not be very busy that time of year also, so that if I have to order items, I have plenty of lead time for them to arrive. I'm going to also be working on doing the proof and the experimental construction in parallel, since there's going to be a lot of downtime along maybe waiting for parts or waiting for the shop to do some welding. I can be working on the proof in parallel with that. And those two activities go well together. The simulation is going to be my focus during the winter months, because I know there's a good chance the creek could be frozen then. It could be difficult to do experiments. Also, it's important that I verify that the controller performs well in simulation before I get outside. Finally, I'll just point out that I did specifically allocate time for documenting both my code as well as writing my final paper, presentation, and poster. So I had 2 weeks that my professor gave me off from class, and I used that time to implement one part of my simulation to work on developing a trajectory generator. And you can see, even though that was just like one box in my previous slide, it's a lot more complicated than that in practice, but I learned a lot in doing so, and I built up a lot of skills I think I'm going to use for the bigger simulation. So in conclusion, the process that I'm going to study is an adaptive velocity controller for an unmanned surface vessel. And the property that I want to show is that it's able to stabilize the velocity, meaning achieve a desired velocity, despite the fact that we have some uncertainty in our drag coefficients. To demonstrate that it does what I say it's going to do, I'm going to combine a proof, which is going to use Lyapunov's method, simulation, which I've begun some work on, and an experiment in College Creek with a 10-foot John boat that I talked about previously, to try to show that this is able to do what I say it is, that this property holds. In terms of novelty, the control law itself is novel. It's entirely new control law, so we're pretty excited about that. The biggest risk is weather and equipment loss. Anytime you work in the maritime environment, that's the case, but we've taken some good steps to try to mitigate those issues. I want to thank everybody for coming to my talk today. I look forward to chatting with you and hearing your questions and comments. Again, I'm Joel Esposito. Have a good afternoon. Well, what do you think about that? Do you think I did better? I think so. There was a lot of content there, and certainly it was longer. But let's go back through some of the things that we saw and talk about some good practices that you can implement in our own presentations. So the title slide. It's important that the title slide give your audience an immediate sense of what it is you plan to talk about. Again, it could sit up there for a while you're introduced. Also, the way audience members have to digest information in real time, it's always good to prep them for what's coming next. A little repetition never hurts. So these pictures are things that everyone can quickly wrap their head around. I also added my contact information on there. And while no one may need it now, it might be good to have later on. I was careful about choosing a title where I defined my acronym and had some more descriptive words. Here, my motivation gives some certainly non-trivial facts. Very few people probably know about the Navy's plan to add 1,200 vessels over the next decade. I showed that I really read about the area and established some expertise. I also had 3 graphics that illustrate, even to the layperson, why it would be so important to control a vehicle's velocity well. When I had to talk about an equation, I used some extra visual cues to help my audience members digest what was going on. I don't recommend putting many equations in your proposal presentation, but understanding, for example, the drag is really important to the whole thesis here. So when I had to, I labeled or color-coded which terms were unknown or uncertain. I also color-coded and labeled what the variable Vx stood for, since it was not obvious. I took that picture that I had in the previous presentation and I made some annotations and I left them up there so that the audience didn't have to remember all this while I spoke. Here you see the same plot you saw before, but I labeled the axis. Often plotting software such as MATLAB, the default font size can be quite small on the axis labels. So I took the liberty of making my own axis labels in PowerPoint and made the font much larger and easy to read. Here I have a graphic that shows why it could be challenging to estimate the drag coefficient exactly, and I spent some time talking through it. The literature view, instead of having a dense slide with page numbers and publishers, I opted for a graphical layout that shows how different sets of work relate to each other, complement each other, or group together. I spent some time calling out where my own work fits in this. Using a last name and a year, or perhaps a short title, is a common way of acknowledging work without having dense page numbers and publisher information. Here, my problem statement lays out the process I intend to study, which in this case is a control law, as well as its inputs and outputs. Whether your process is a control law, a filter, an estimator, or an algorithm, it's good to spell out what the inputs and outputs are. Presumably, you want to study this process because you think there's something good or interesting about it. So that's where the property comes in. I just described the property that I want to show holds true. My whole demonstration focuses around showing that I can achieve the 0 steady state error with 10% uncertainty in the coefficients. I showed here visually what that might look like. Even though I haven't done the experiment yet, this shows you kind of an example result that I might get. It can be challenging to talk about math and proofs, especially when you haven't done them before, but I do recommend including an outline along with some kind of graphic to show what the strategy is. If it's dense and it requires many steps, a step-by-step reveal can actually be a useful animation. If you're going to put an equation up, take a couple minutes to talk through what some of the variables are and why they're important. If you don't have time to do that, perhaps reconsider using the full equation. For a simulation, if you plan to do a simulation or an algorithm, a flowchart, pseudocode, or a control systems diagram can be very useful. You can think about each block, not just for your audience as a way of explaining what the different subsystems are, but even for you, it's a map of the pieces of code or the subsystems you'll have to develop. It's important to label the signals on each of the wires and to give your audience a sense of the set of simulations or experiments you plan to perform. If there's multiple factors you're going to combine or vary, a table can be a useful format for that. Here on the experimental platform, instead of showing a dense parts list with model numbers, I had small graphics of each of the items that I plan to use, and I showed how they fit together or interconnect. Again, at this stage, you might not have all the details worked out, but you should at least know what the overall architecture is and be able to label what information will be passed back and forth along each connection. Whatever it is that you plan to show, you need a way to establish ground truth. You need a way to establish that your system does, in fact, do what you say it does. So at least one slide should be dedicated to how you will know your answer is right when it's done. And for me, that was the use of this real-time GPS system. If you're going to do experiments, it's good to have a cartoon-like depiction of what it is you plan to do. And it's good to have a recap at the end showing how those pieces fit together. We talked about some of these issues in class, the pros and cons of different types of demonstrations and how they can complement each other. Try to mimic that language if possible. Every project has risks and they should be spelled out. At the very least, you should talk about your time risk. Time is the most valuable commodity that you have, and it's the most constrained. So be sure to address those issues. Also, for any project involving human subjects or autonomous vehicles operating in the wild, you should discuss equipment loss and safety. But there might be other considerations or technical risks you'd like to discuss as well. You don't have to use the Navy's risk management matrix, but it does provide a nice way to think about classifying your risks and moving them from one category to another. Budgets can be challenging to talk about, but here I made the budget occupy the entire slide, and I omitted the title because I believe it's obvious from the context. So now the font is much, much larger and easier to read. I know that most people care more about the materials, even though these other components are true costs. So I decided to make a second slide that kind of zoomed in on that and discussed the out-of-pocket expenses. Here I took the dense timeline you saw before, and I made a much lower resolution version of it. And I thought through my talking points, what is it that I want to say about it? How did I design this timeline to minimize my risk or maximize my productivity? Is there anything unique or special about it? Perhaps there's some milestones that I have to hit. Think through what you'd like to say about that. If you've gotten preliminary results, you should show them here. It gives the audience a lot of confidence that you can actually do what it is that you're going to say you're going to do. The conclusion slide, there's a variety of ways to write it, but since this is for proposed work and not completed work, I think it's good to recap the problem statement. What's the process you'll study? What are the properties that you claim it holds? And how are you going to design your activities, your demonstration plan to show that? I think it's also good to reflect on what's novel and what your biggest risks are and how you intend to address them. If this was completed work, I might also have some ideas for future extensions as well. Again, I have relevant graphics here that illustrate some of these points. Now, one strategy to end the talk is I could easily end on this slide, and I think that's not a bad choice. Right? It leaves my problem statement up. It's got some interesting graphics. It says what's interesting about my work, and perhaps it even anticipates some questions from the audience. Another strategy for your conclusion slide would be to go back to your title slide, perhaps modified. At the least, this provides a nice backdrop for your Q&A session. It includes contact information in case someone runs out of time or feels too shy to ask you a question personally. They might want to send you an email. It includes some graphics that I might need to talk through when an audience member asks me a question, for example, about how I plan to conduct one of my experiments. It leaves my title up there to prompt audience members who perhaps zoned out during the talk. So in my opinion, this was a much better presentation. You don't have to incorporate all these tips. Certainly there's room for your personal style here, but think about these things. Think about making each slide as valuable as possible, either motivational, interesting, entertaining, or informative. But don't waste valuable real estate on your slides, and don't use 2 or 3 filler slides like a blank title slide, a question slide, and an outline. I'll leave this up on the screen. I know it's a bit small, These are some summaries of tips that I have for giving presentations, and I'll drop this in the comments and the description as well. Thanks for your time today. Bye.